Okay, guys, last example, example 9. F of x is equal to x minus 1 squared, x minus 3 over x squared. So remember, x cannot be equal to 0. I would just get a feel for this question first of all. The degree of the numerator is 3. And the degree of the denominator is 2. So it's 1 more. So there must be an oblique asymptote. There's also going to be a vertical asymptote because that doesn't cancel out. Okay, so find the coordinates of the intercepts. What if I let y be equal to 0? Remember, you're solving where the numerator is 0. So I get 0 is equal to x minus 1 squared times x minus 3. So obviously x is 1 or x is equal to 3. Okay, so it goes through 1, 0, 3, 0, and x cannot be 0. So there is no y-intercept. Vertical asymptote occurs. Okay, well, that doesn't cancel over there. So your vertical asymptote will be at x is equal to 0. Okay. To find the oblique asymptote, I'm going to have to now multiply out and then divide. So when I times that out, I get x minus 1 squared becomes x squared minus 2x plus 1. If I distribute the x and the negative 3, it ends up being x cubed minus 5x squared plus 2x plus 7x minus 3 over x squared. Okay. Right, now I've got to do the division. You don't have to do that force and balance here because it's just dividing by x squared. Normally we're dividing by 2 terms and you have to do the balancing. Okay, but then we're dividing by a single term. X cubed divided by x squared is x. Minus 5x squared divided by x squared is just minus 5. And then you're going to be left with plus 7x minus 3 over x squared. So the division here is pretty straightforward. Okay, so your oblique asymptote, well, what's your answer? It's x minus 5. So your oblique asymptote is going to be at y is equal to x minus 5. Now remember, there was no factor in the denominator which cancelled with the numerator, so there are going to be no removable discontinuity. Okay. Then it says that determine the coordinates of any stationary points of f that exist. Well, again, I would work with this format that you've got after your division. It's much easier to work with. So you get f of x is equal to x minus 5 plus 7x minus 3 over x squared. Stationary points occur when the derivative is equal to 0. So you've got to find the derivative of that whole thing over there. The derivative of x is just 1. The derivative of negative 5 is 0. Then I'm going to use the quotient rule to find the derivative of 7x minus 3 over x squared, which gives us 7 times x squared minus 2x times 7x minus 3 over x to the 4. I just moved that 1 to the other side, and I've got it equal to negative 1. Multiplied by x to the 4, so I ended up with that. Okay, moved everything to one side. So I've got to figure out where x to the 4 minus 7x squared plus 6x is 0. Take out x as a common factor. So, but x cannot be 0, remember, because that's a vertical asymptote. So I've got to solve where x cubed minus 7x plus 6 is equal to 0. To do that, I'm just going to use my calculator. Okay, and I've got x in equation mode. X is negative 3, x is 2, x is 1. When x is negative 3, if we sub back into that equation, we get a y value, which is equal to negative 10,7. And if x is equal to 2, we get a y value of negative 14. When x is 1, y is equal to 0. So there, my 3 stationary points over there. Okay. Now, if they ask you to show algebraically where a function is increasing or decreasing has to do with the derivative equation. A function is increasing when f dash x is bigger than 0. Okay, that's when it's going to increase, and it's going to decrease when f dash of x is less than 0. So you're going to be solving an inequality with the derivative equation. So f dash x, we know from over here, okay, we found the derivative. It's 1 plus the derivative of that, so that's that 1 over there. So it's 1 plus, and then the derivative of 7x minus 3 over x squared became this whole thing, 7x squared minus 14x plus 6x over x to the 4. Okay, can't get rid of the denominator because that's only when it's equal to 0. But times that by x to the 4. Okay, so in the previous one we got rid of the denominator because it was equal to 0. Now we can't. So I end up with x to the 4. That simplifies to minus 7x squared plus 6x. So you get x, x cubed, the x's cancel, and we left it just x cubed in the denominator. These factors are simply got from the fact that we know that the solutions to this cubic earlier, x cubed minus 7x plus 6, is x is negative 3, x is 2, or x is 1. So because x is negative 3, the solution, x plus 3 must have been a factor, x is 2, or you could do it again on your calculator, I guess. Okay. So x minus 2 and x minus 1. Those are your factors all over x cubed, your critical values, negative 3, 2, 1, 0. So negative 3, 0, 1, 2. Make sure there's no squares, so you can alternate. Make sure you get the first one right. Sub in a number less than -3 into this thing over here. You'll get negative, 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 negative. The whole thing is positive. There's no squares, so you can alternate positive, negative, positive, negative, positive. Okay, so I've highlighted in blue where the function is increasing, where things are positive. The gradient is, remember, these are gradient values, not y values. So the derivative is going to be increasing. In other words, the derivative is going to be positive. Well, first of all, when x lies between minus infinity and -3, then when x lies between 0 and 1, and then when, for all x values bigger than 2, and likewise will be negative when x lies between -3 and 0 and between 1 and 2. So if you're ever asked to find out whether something is increasing or decreasing algebraically, that's the strategy you're going to use. You can use solve an inequality involving the derivative equation, right? So next thing we're asked to do was to sketch the function. Okay, remember this function, a summary of it, it had intercepts at 1, 0, and 3, 0. We worked out there's a vertical asymptote at 0. Okay, oblique asymptote y is equal to x minus 5. Those are the intercepts of that. Stationary points at 1, 0, 2, -1/4, and at -3, -10,7. So I draw in the asymptotes first. There's the line x is equal to 0. Here's the line y is equal to x minus 5 with its intercepts at 5 and -5. Draw those in first. Then I draw in the stationary points and the intercepts. Stationary points, I would remind yourself that these are stationary points. A stationary point at -3, -10,7, another stationary point at 1, 0, and another stationary point at 2, -1/4. So you remind yourself the graph has to turn there. There's an intercept which is at 3. Okay. So when I start to draw the thing, even if I didn't have, I'll show you how it relates to the increasing and decreasing just now. It must tend towards the oblique asymptote, turn at the stationary point, head towards the vertical asymptote. Okay. Over here, okay, it heads towards the vertical asymptote, turns at the stationary point, turns again at when x is equal to 2, passes through 3, and heads off towards the oblique asymptote. If you go back and have a look, okay, the blue part is where the function was increasing from the previous page. So it was increasing for x values from -infinity up to -3. Then increased again, you can go check on the previous page, from 0 up to 1, and then increased again from 2 to infinity. The function decreased, in other words, f dash x was less than 0, from -3 up to between -3 and 0, and between 1 and 2. As I say, you can go check that on your previous page. Guys, that's about as difficult as it gets. There are these things for Mindborn. If you want lots of practice, it might be a bit too much. Okay, I have put up on Teams some past paper questions with their memos. Okay, it's in the rational functions folder. Okay, I hope that, but if you understand this pack of notes, honestly, you should be fine. Thank you. All right, good luck with everything. All right, we're going holiday now. Okay, stop recording.